Hello, today I'm going to be going over how to create an animation like this where points are moving on a curve network and they have these trails. So I've got a curve network like so, and then I've also got a point cloud, and I want to move these points along this curve and create trails. So there's a few steps I can break this down into. The first step is to find the path that these points need to travel. So since I only know the start point, which is these points right here, I need to pick some length for them to travel, and I've just set this as a constant value of the motion length right here, but it could be different for every point. I need to set some distance to move along this primitive, and I need some way to find that. And I'm going to store those primitives that it needs to move on in an array, like so. So this is a pre-computed array, so it doesn't compute every time in the solver. And then in the solver, we're going to move the points along these primitives, and then once we've reached the end of this primitive, we can move along the length of this next primitive, and so forth. So that's the first part, and we're going to use depth first search to do that. Now, in the second part is just the solver itself. So, quick preview, we're just going to be moving along those primitives like so, and then the third step is creating the trails of a specified length right here. And that's really simple to do since we just have already this array of primitives, so we can just cull the endpoints once we reach the desired length. And then the fourth step, which sort of just depends on the data you have, is right here. You'll notice my curve network is not evenly segmented, but what I'm actually doing in this loop is I'm adding all of these points procedurally using polysplit based on the crash location point clouds over here. So you'll notice this is the point cloud, and before the loop there's no points here, but then I'm adding all of them corresponding here, and I'll be going over that after I explain depth first search, so it sort of makes sense why I'm doing this. Okay, so to do that and give a quick example, I've got this small abstracted piece over here, and I'm going to just turn on all of this. So basically the situation we have is we have a point somewhere right here. So this is from our secondary point cloud, and we have a specified length. So the specified length could be 6. So let's say we want to move a length of 6. So we want to move length of 6. So to do that, we need to look for paths to travel since we only have the start point. If you had a start point and an end point, like here, you could just use a shortest path SOP or a shortest path algorithm, and then just connect these 2 points looking on this primitive path. But we don't have that. We only have the start point, and we have to backtrack, and that's why you'll notice I'm playing this animation backwards, not forwards. All right, so again, we have our start point here in the red, and we're looking for a length of 6. So to do that, we need to go on this curve network, and we're going to look towards the end nodes of the primitive. So here we'll look to the end node, and we'll look at 0.5, and then we say, have we traveled a length of 6 yet? If we haven't, we keep looking, and then we keep looking, and we keep looking, and every time we get to a new node, in this terminology, I'm calling nodes the endpoint of a polyline. So if this is a polyline, there could be internal points. The nodes are just the endpoint right here and right here. So we're ignoring the internal points. And then so we're going to keep looking and keep looking. And then if we hit a dead end and we haven't reached a length of 6, we need to jump back down to the root and then keep looking here. And to do that, I'm going to use something called depth first search, which is a form of graph traversal. And how this is going to work is we're going to have some starting point. So let's say our starting point is 4. And in a later video, I'm going to talk about how I split these polygons procedurally with polysplit to add vertices. So let's say our start point is 4. How this is going to work is we're going to have an empty variable or an empty array to start out called stack. Or it's not going to be empty, it's going to be equal to our start point, which is 4. And then we're going to have an array called visited. And the stack array is going to hold all of the candidate nodes. So all of the neighbor candidates that we're looking at. And this will make sense in a second. So I'm going to go and step through the iterations one by one. So how this is going to work is if our start node is 4, we're going to pop the last value off the stack. So in this case, that's 4. And then we're going to look for all the neighbor nodes. So in this case, we don't have anything on this way. The only neighbor node is 5. So at the end of this iteration, the stack will be equal to 5 and visited will be equal to 4 because that's the node that we visited. And in the second iteration, we're going to go and we're looking at 5. So visited will be equal to 4 and 5. And the stack will be equal to the neighbor nodes, which is 6 and 3. Okay, so then stack will be equal to 6, 3. And then the third iteration, we're only popping the last value off the stack. So in this case, we're popping 3 off the stack. So visited equals to 4, 5, 3, and stack is equal to 6, and then 7 and 0, because those are the neighbor nodes of 3, 7 and 0, and 2 as well. All right, so let's say we have 2 at the end. Let's go to iteration 4. Stack is equal to 6, 7, 0, and we pop 2 off, so visited is equal to 4, 5, 3, and 2. And 2, we see, okay, the only neighbor node of 2 is 3, but 3 is already unvisited, so we don't do anything, and we pop 2 off the stack, so now we jump all the way back, and we're looking at 0 now. So in the next iteration, in iteration 5, stack is equal to 6, 7, we pop 0 off the stack, visited is equal to 4, 5, 3, 2, and 0. And since 0 has no neighbors except for 3, which is already unvisited, we jump back and now we're looking at 7. So on iteration 6, stack is equal to unvisited is equal to 4, 5, 3, 2, 0, and 7. And stack is equal to the neighbors of 7. So now we're looking at 6, 1, and 12. So the same thing happens. And if we reach only dead ends, you'll see we'll jump all the way back down to 6, which will be here, and then we'll start traversing up this direction. So that's how depth first search is going to work. And then a quick other thing we're going to add, we need some way to check the length, and to do that, we're going to be storing dictionaries. So how this is going to work is we're going to have 3 dictionaries, one called prim map, one called node map, and one called length map. And what this is going to do is it's going to store the node in the prim map, the node map, and the length map. It's going to store the node. So remember, the node is these endpoints of the polylines, and the child relationship. So what this means is if our start point is 4, in the next iteration we're moving to point 5, or node number 5 in this case. The relationship of this is going to be a parent, so in this case 5, of the key value, and then a child value of 4. So notice it's dependent. Since we're moving this way, the parent is 5 and the child is 4. So let's say, for example, we were starting at point 8 instead. We point 11 and 12 would have the node map values. So this is for the node map dictionary of 11 to 8 and 32 to 8. So different key values but same, or different keys but same values. And then what this is going to allow us to do is backtrack. So let's say, I'll go back to the example where we're starting on point number 4. So we'll have a value of 5, 4. And then let's say we move to point number 3. So that would be 3, 5. And then let's say we go to point number 2, and then it's 2, 3. What this allows us to do is if we reach point 2, and this is our endpoint, and we've reached enough length, we can backtrack and say, okay, the child of point 2 was 3, and then it goes and we look for that key value, and that returns 5. So that allows us to backtrack and get the path that we've traveled, which is this. And then the prim map is just going to store these prim numbers instead of the node numbers, and then the length map is just going to store the length of those primitives, and that's going to allow us to iterate through those dictionaries every loop and check if we've reached the desired length. All right, so now I'm actually going to go onto the implementation. To do this, in the first stream, I'm going to be plugging in my point cloud, so that's going to be here, and in the second stream, I'm going to plug in my curve network. So again, my curve network looks like this, and my point cloud looks like this. And before this point wrangle, that I'm going to do all the depth first search in and calculate the arrays of primitives to travel, I'm initializing and storing as an attribute the motion length. So this is that length, the physical length on the primitives that I'm checking for. So I'm checking this against the measured length of the primitive. So I've also got a measure stop here, and I'm just storing this as a length value on all the primitives. So this is what I'm going to be using in that length map dictionary. So right now this is just a constant value, but this could also be different for every point. It doesn't really matter. All right, so the first thing I'm going to do is I want to grab that target length. So I'm going to call it target length. This is equal to the motion length variable. So that's what I was just saying. I initialized up here, motion length, and that is currently a value of 6. And then after that, I'm going to grab the start point. So int start point is equal to near point, and I'm looking for the nearest point on the first input stream, which is the curve network from the point cloud position. So this is going to grab the start point, and as I said earlier, I'll be going over how to procedurally polysplit in a second video. All right, so after this, I'm going to create my stack, which is going to be equal to the array with the value of just start point in it to start out with. And I'm going to create an int array called visited, and this is just going to be empty. All right, and from here, we're going to continuously loop in a while loop and just say while the length of the stack is greater than 0. So as long as there's values in the stack, we're going to be looping through this. And after that, we want to grab the current node. So the current node is equal to pop stack. So this is going to remove the last value from the stack array, as I was showing earlier, and then store it into this node variable. And then I want to check to make sure we haven't already visited, and I can do that using the find function. So I'll say find, and the first thing we want is to look for the array that we're searching in, and then the value that we're searching for. And if it's less than 0, so that means if it's a negative number, find will return a negative number if the value isn't found. So if the value is not found, we're going to go ahead and say that, okay, we visited it now. So we'll append node to the visited array because we've now visited it. And then I can start grabbing all the neighbor nodes. So to do that, I'm going to create an array called neighbor prims. And this is going to be the array of all the primitives connected to the current node point. So this is on the curve stream, point prims, like so. So this is going to return, for example, if we're looking at here and our start point is point number 4 right here, the neighbor, the prims connected to this point is only point number 2. So it's important that, for example, if I was starting on point number 5, the neighbor prims would be 2, 4, and 1. So it's important that you make sure you fuse all these polylines together so that there's not actually 2 points here and these primitives aren't connected. All right, so after this, I'm going to iterate through. So I'm just going to say for each int prim and neighbor prims. And then here, I want to grab all the points on that prim. So I'm say int prim points is equal to prim points 1 comma prim. Need to make this an array. All right, and then after that, I need to grab the endpoint and the start point, since how I was talking about before, I'm not counting the interior lines on the polygon. So I've got a polyline like this, for example, and it could have all these interior points. I only want the endpoints right here and here. So to do that, I'm just going to say int, I'll call this segment start point, and this is equal to just prim points 0, and then I'll say int seg endpoint is equal to prim point -1. So all right, like so, and this is just going to return the start point and the end point. But the problem is that these could be in any order, since this is a really unorganized. There's not a lot of rules that this curve network. There's not really any rules that this curve network is following, since it's just a street pattern. So I need to make sure that I've selected the proper point for the end. So to iterate that again, so let's say, for example, I'm starting on point number 8, and these red dots represent internal lines. If I'm getting all the prim points on polyline number 7, and my start node is this point right here, I need to make sure that my start point could either be this point or this point. I need to make sure I'm picking the point that's furthest, that's not equal to the current node we're searching at. So either one could be it. So I just need to create a quick conditional statement. And to do that, I'll create an uninitialized variable just called neighbor node. So this is going to be a target neighbor node. And I'll just say if the seg start point is equal to the neighbor, or is equal to the current node. So if the start point is equal to the current node, I want to say neighbor node is equal to the segment endpoint. So what I'm saying here is that if these 2 points are the same, pick this point, and then I'm just gonna do the opposing statement saying neighbor node is equal to seg start point. So that'll take care of that. And then from here, I just want to check if we've already found this neighbor node or if we've already visited it. So same thing as earlier, if find visited, comma, neighbor node is less than 0, then we can append it to the stack now. Stack. And then from here, this takes care of basically the first part of depth first search. So this is going to iterate through these curves, and now we need to implement the checking of the lengths with the dictionaries. So to do that, I am going to create 3 dictionaries out here. I'm going to create the prim map dictionary and the node map dictionary and the length map dictionary, like so. And then from here, I want to go down back into the neighbor node loop. So here this is where we're saying, okay, this node is valid. We can actually search on this node. So to do this, I want to start adding values to these maps. So first I'll start with the node map actually. Node map, and then we want to set the key value. So the key is equal to the neighbor node. And then the value is equal to the current node. And this returns a value because the key needs to be a string, so we can just use I to A to convert A into a string, like so. So remember what this is doing is this is creating a dictionary value of, for example, if our start point is 4, and if this neighbor node is equal to 5, this is going to store the value of 5 to 4 in the dictionary. Okay, and then for the prim map, going to do the same thing, but instead I'm going to be storing the prim. So I'll say prim map I to A neighbor node, and this is equal to the prim. So same as the node. In this example, this will be storing a value of 5 to 2. So these values right here. Okay, and then lastly, I need to get the length value. So I'll say float prim length is equal to, we're reading the length value that I got with the measure sop earlier. So length, and then we're reading on the current prim that we're looping through. And then after this, I just want to add this to the map. So I'll say length map I to A neighbor node is equal to prim length. All right. So now we've stored all the values in the array. We need to now check, or we stored all the values in the dictionary. We now need to implement a way to every iteration. We need to check what position we're at and then backtrack. So basically every iteration of this while loop, we're grabbing the next value off the stack, and we need to backtrack through those dictionaries and see the path that we've traveled so far. So to do this, I'm going to create a float length and initialize it to 0. And this is going to count the total length as we're backtracking through this array or the dictionary. And then I'm also going to create an empty array called primPath, and this is going to store the primitive numbers that we've traveled. So let's say we end up at point number 3 and our starting point is 4, so that means our path of travel went like this. This is going to store the values 1 and 2, and the length value is going to increment by the lengths of primitive 1 and the lengths of primitive 2. And then after that, I'm just going to create one more variable called the, and I'm going to call it the current point. So I'll just call it cur point, and this is going to start out being equal to the node. And then I'm going to drop down a while loop and say, well, the current point is not equal to the start point. And what this is going to do is say that. So again, let's say we ended up at point 3. So we're going to backtrack until we reach the start point. So while the current point, which is starting out, is the current node, which is 5, is not equal to the start point, we'll backtrack. So in the next iteration of this while loop, let's say we go back to 5, not equal to the start point, we go back to 4, and then we're done. All right. So the first thing I'm going to do in here is get the node child. And this will be equal to the node map. And then in here, it's going to be the current point that we're reading in. So just to make this clear again, since this can be a bit confusing, if we've taken this path right here and we've ended up at point 3 and started at point 4, we have the dictionary values in the node map are equal to 3 to 5 and 5 to 4. So in this case, the current point is equal to 3 right here. So the child node will be equal to 5 since we're reading the key of 3, and that returns the value of 5. And then the next iteration will read the key of 5, which will return the value of 4. All right, and because of that, I'm going to update the current point to be equal to this child node, so that on the next iteration, we'll read the key value of 5 instead of 3 again. But before that, I'm also going to read in the child prim, which is equal to prim map way, and then of the current point. And then I also want to read in the length map, and I'm just going to increment the length value that I stored above. So I'm going to say plus equals to the length map of the current point. So every iteration, this is going to increment the length value by the length of these primitives. So first it'll increment by a length of 1 and then by a length of 2. And then we're going to check against that value later. And the last thing I want to do is append to the primPath array that I created earlier and add the child prim to that. And I'm adding, and I'm creating this array and I'm appending to it because if we found a path of the desired length, we're going to save out this array as the array that we need to travel for the points. All right, so now this is done. I just need to create a single conditional branch and say if the length value is greater than or equal to the target length, we can break first of all, but then as I was saying before, we've stored these valuables or these values in the prim. So we need to create an array called prim sequence, and this will be the actual array that we're going to, the actual primitive array that stores the path we can travel. And here I'm just going to set the prim sequence is equal to the prim path. All right, so I'm going to let this cook, And once this is done, we should, or actually I need to actually write out the array. So down here, so like so, at prim sequence is equal to prim sequence. And I'm actually going to reverse this array because in here we were tracking like this. So we're actually tracking backwards. So for every node we're going backwards. So we're storing this array first, and then we're storing this primitive value in the array. So primitive 1, and then primitive 2. But then when we want to go to move the point, we need to move on primitive 2 first, and then primitive 1. So I'm just reversing this so that it's ordered. All right, and you can see here we've got our prim values corresponding for all of these points. And then after this, we can go into the solver and start moving the points. All right, so now I'm going to get into the actual implementation of the animation. And in the first input of the solver, I'm going to bring in the points with the depth first search that we did, and the second input is going in the curves. And before I get into the solver, there's a couple things I'm going to explain about how this is going to work. So basically, we've got some polyline. I'll actually just visualize it on here. So we got some polylines like so. And if this is our start point, for example, and let's say the length of this primitive is equal to 1. So we've set the motion length variable on the points to be equal to a constant value of 6. So that means we're moving a total length of 6, and then we need the number of frames or how much time we want to move that in. In this case, I'm just doing 1 second, and my scene FPS is 60. So what I'm going to say is in 60 seconds, or in 60 frames, move 6. So we're going to move a distance of 6 in 60 frames, which is equal to a distance of 0.1. So every frame we're going to, if our point is starting here, and the next frame we'll move 0.1 to here, and then the next frame we'll move 0.1 to here. And every time we're checking to see if we've reached the end of this primitive. And if we have, we go on to the next primitive in the prim sequence, and we're going to interpolate the position on this curve between the 2 points. All right. So to implement this, I'm going to drop down another point wrangle, and this is going to go outside the solver, and this is going to be just like initializing variables outside of a loop so that we can increment them. So first I'll have a prim index, and this is going to start equaling to 0. So this variable is going to define what primitive we're currently at in the prim sequence. So we're starting at 0 because we're starting at the first primitive here. And then once we get to the end of that, we can increment the prim index to whatever primitive we're on. And then I'm also going to create another variable that's a float, and it's going to be called UV star offset. And this is going to also be equal to 0. And what this is this going to be the UV value that we need to interpolate on the curve. And for this, I'm using manually specified UVs, not intrinsic UVs. So I've got this arc length spine here. And the reason I'm doing this instead of using intrinsic UVs is because here I've got an unevenly segmented curves right here. And that means that if we used intrinsic UVs, the points would be, or the UV value would be weighted, and we wouldn't get proper interpolation. So quick, I'll just go over intrinsic UVs. If we have a polyline like so, and it's got uneven segments like this. So intrinsic UV values is equal to 1 divided by n minus 1, where n is the number of vertices. So this is 1, 2, 3, 0, 1, 2, 3, 4 vertices. So it's 5 vertices. So 1 divided by 4 is equal to 0.25. So that means the UV value will look like this: 0.25, 0.5, 0.75, and 1. So you'll notice is that even though the length here is much greater than the length here, the step between the UVs is always 0.25. So when we go to interpolate, if we want to interpolate the point position at a value of 0.75, let me actually do something like this so it is a little more clear. So let's say I wanted to interpolate the position at 0.75 UV on the curve. You would think that would give you a value somewhere here, but using intrinsic UVs is actually going to return just whatever point has that value. So that's why I'm using manual UVs instead of intrinsic UVs, because I don't want to have to resample, add a ton of points, and potentially lose some accuracy in my geometry. All right. So now that that's done, I'm going to go back to here, and I've got the UV star offset, and these are the only two variables I need right now. I'm going to go inside of my solver and add a new point wrangle with the first frame going into the, or the first input going into the previous frame, and the second input is the curve network, like so. And in here, I'm going to create a first, this can actually be a float, because we're going to be dividing floats by it, so it doesn't need to be an int, and this is going to be the FPS, so I'm going to get the scene FPS by grabbing the at time increment variable and dividing by 1, and because of floating point position, I'm just going to seal it, and this will return whatever your scene FPS here is. So this should return a value of 60. All right. After this, I just want to create another float called the step length, and this is going to be equal to the motion length divided by FPS. So this is going to be the value of 0.1, as I was saying earlier. So this is the physical distance we need to move the point along the curve every frame to reach the desired length, which is 6. And then after this, I'm just going to read in the UV start offset. So UV start offset is equal to at UV start offset. So I'm just reading this in, so it's a little bit easier. And then I'm going to create an int prim, and this is going to be the current prim that we're on. So this will be equal to, also need to create the prim sequence. So I'm going to create an int prim sequence array, and this is equal to that prim sequence. So this is the array of prims that the path, the point will move on, and then the prim is equal to the prim sequence with the current index. And we can just say int x is equal to app, like so. And this always seems to not like it whenever I use ints, so I have to specify it. All right. So this is reading all the variables in, and then I want to create a float variable called UV step, and this is going to be equal to the step length divided by the prim length. And so to do this, I need to create a float variable called prim length, and this is going to get the length of the current primitive we're on. So I'm going to say prim, read from the curves, value of length with the current prim. So the UV step is the percentage on the UV we need to move. So like I was saying before, if I have a polyline like this, and there's a point right here and right here. Here we're using manual UVs, so this will actually be correct. This will be something like 0.0, this will be 1, this could be like 0.75, 0.5, and 0.45 or something. So what I'm doing here is I'm taking the step length that we're moving, 0.1, dividing it by the total length of the primitive, and this will return the UV percentage that we need to move on the specific prim. So because we're moving a constant value of 0.1, but the length of the primitives changes, this will be different for every prim. So that's just why that variable is being created. And then I'm going to create a float variable called available length, and another float variable called target UV offset. And so the available length is going to be the length that's currently left on the primitive to travel. So for example, if I have a polyline like this, and I've moved all the way to here, and I need to move a distance of 0.1, right, every frame, so 6 divided by 60. If this distance right here is less than how much we need to move, I need to jump on to the next prim in the sequence, so right here, for example, and then move across, and then move on that primitive, interpolate the position on that primitive instead of this, because there's not enough space left. And the target UV offset is just the value that I want to interpolate at. So for example, primitive right here, if I interpolate the value, the position value exactly at 0.5, a UV value of 0.5, it should give me the position directly between these 2 points, or at 0.2. So that's the UV I'm interpolating from, since the UV will always be between 0 and 1. And I'm using that manual UV for that. And here is there's sort of a problem you'll run into by doing this, is because we're using manually specified UVs, the UVs have an inherent direction and the primitives. So for example, on these primitives, the UV value on one primitive, since I'm storing the UV value on the vertex, so this point could have multiple vertices. So for example, if this is one prim right here, and this is another, and this is the prim right here below it, so this is that, and this is this, this could have a UV value of 0 and 1, like so, and then this could be reversed. This could be 1 right here, and this could be 0. So if our starting point is here, and we interpolate the position at 0.75, we'll interpolate the position here, which would be correct. But then if we try to interpolate the position here at 0.1, it's going to interpolate over here, when really we wanted it to be the complement at 0.9 on this side. So we need some way to work around that. And what I'm going to do is do something similar to the depth first search. Is instead of doing this all in the solver, I'm just going to pre-compute an array that matches the prim sequence array that stores a 0 or 1 value, and just 0 means it's reversed, and 1 means it is going 0 to 1. So I'm going to start by dropping a point wrangle right below the depth first search. And in here, I'm going to start by grabbing the prim sequence. So I'll say int prim sequence is equal to at. This is an array is equal to at prim sequence. And this needs to be type specified. And then down here, I'm going to create an empty array called UVDirs. And this is going to be the array that I'm going to write out in the end. So I might as well just say I at UVDirs is equal to UVDirs. So right now this is empty. And then I'm going to create a vector, and this is going to be the sample position. This is going to start by being equal to the current position of the point. So basically what I'm going to do here is, if I've got the polyline, and this is my start point, so I'm starting off with a sample position is equal to this point, I'm going to get all of the vertices on this current primitive, the first prim in this prim sequence, and then I'm going to check, okay, is the UV value at the end equal to 0 or 1? And then I'm going to set this to be the sample position, and then I'm going to check the next, say is this 0 or 1? I'm going to check the next and keep going forward, and that's when I'm going to get these values into an array. All right, and to do this, I'm just going to loop through. So I'm going to say for each int prim, and the prim sequence, I want to get the prim length, or first I want to get the prim vertices. So I'll say prim verts is equal to prim vertices on the second input and on the current prim that we're looping on. So this will return all the vertices. So I need to make sure I plug the curves into the second input. After that, I want to get the end vertex. So int end vertex is equal to prim verts -1, int start vertex is equal to prim verts 0. So this will return both the endpoints, and then I want to get, or both the start vertices, and I want to get the start point. So I'll say int start point is equal to vertex point, and this is going to be 1 comma start vertex. So this will return the point that corresponds to the vertex, and I'm going to use this to grab the positions if I need them. So this will be the end point is equal to vertex point 1 comma end vertex, like so. And then after this, I can create, actually I can do all of this in some branches. I do want to grab the start position. So start point position is equal to the need to read the point value. So this is going to read the position of the start point, and then I'm going to do the same for the endpoint. So vector endpoint position is equal to the point 1 p endpoint, and then I want to grab the distances between these. So I'm going to say float dist to end is equal to distance between the current sample position and the endpoint position. And then I'm going to say float dist to start is equal to the distance of the sample position and the start point position. So now I've got a single primitive like so, and if this isn't the current position that I'm starting on, I now have the distance. I now have this polyline up here. I have the distance to this point and the distance to this point. So in this case, this distance is just equal to 0, and I'm going to use that right now to make sure I'm picking the faraway points just with a couple conditionals. So I'm going to start by saying if the distance to start is less than the distance to the end, I want to first initialize a variable here that I'll call vector start UV, and this is going to be the UV value at the current vertex that we're on. So we'll say start UV is equal to read the vertex value. So this is going to read the manual UVs that I specified with the UV texture SOP, and then I'll say start vertex like so. And then I want to set the sample position equal to be the endpoint position, because now we're now setting it to be this point. And then the else statement is just going to be the opposite. So I'm just going to say the start UV is equal to the vertex UV value of the end vertex instead. And then the sample position will be equal to the start point pos. Like so. All right, and then after this, I just want to drop down one more conditional and say if the start uv.x is equal to 1, so I'm going to append uv_dir, comma 0. So this is setting a 0 value if the start point is 0, and then else I'll just say append uv_dir, comma 1. So what I've just done right here, and you can see it's written out properly, is I'm saying if this point has a UV value that's equal to 1, we know that it's reversed. And then if this has UV value of 0, we know that we're going from 0 to 1 on the UVs of the current primitive. All right, so that's all that's being done there. Now I can go back inside the solver and start completing this implementation. So this is important here because the available length and the target UV offset are going to be different depending on the direction of the UVs, and this can get a little bit confusing. So first I just want to read in that UV directions array, so I'll just say int uv_dirs is uv_dirs equal to uv_dirs Then I need to specify the type. And then I want to say int uvdir is equal to uvdirs, comma, prim index, like so. So this will read the current UV direction of the primitive that we're on. And then I'm just going to drop down a couple conditionals to initialize the available length left on the prim and the target UV offset. So here I'll say if the UV direction is equal to 1. So this is if it's moving positive, the current point we're at to 0, and we're moving from 0 to 1 in the UV direction. I'll set the target UV offset to be equal to the UV start offset minus the UV step. Okay. And then I'll set the available length to be equal to the prim length minus the prim length times the UV start offset, like so. So remember the UV start offset, if we have a polygon right here, if we're starting and this is a UV value of 0, this is UV value of 1, since the UV direction is equal to 1, it's positive. Let's say we're interpolating, and let's say this has a prim length of 1, so length, or let's say 10. Let's say this is a length of 10. We're interpolating at value 0.75. Okay, so this is going to return the prim length times the UV start offset, which is equal to 7.5, and then we're taking the prim length, which is 10, minus 7.5, which is equal to 2.5. That's how much distance we have left to move. Okay. And then I'm just going to do the inverse for if the UV direction is 0, or the complement. So I'll say else and then the target UV offset will be equal to the UV start offset minus the UV step. And then, so you'll notice, or this should actually be the inverse. So up here it should be plus the UV step because the UV direction is positive. So if this has a distance of 10 and I want to move, let's say the UV step is 0.1 and we're moving positive, so now we'll be interpolating the value at 0.85. Whereas if we're moving backwards from 1 to 0, we want to subtract. So if we're moving a UV value of 0.1, we're moving to 0.65. So that's why I'm doing that. So yeah, this should actually be positive in the UV direction, and this down here will be negative. And then I'll just set the available length be equal to 1 minus the UV start offset, so getting the complement of that there. And then I'm going to enclose this in parentheses, make sure it's set to equal to, and then I'm going to multiply the prim length just like I did above, and then lastly I need to subtract the prim length, so I'll say prim length minus. So this will do the opposite of what we did up here. Now that that's done, I can create the conditional branch or the while loop, and this will deal with any time we don't have enough length left on the primitive. So if the available length to move on the current primitive is less than how far we need to move the desired amount, we need to look through the next primitives continuously until we have achieved enough length. So let me just sketch this out so it hopefully makes sense. So if we have polyline like this, and let's say the length values are like so. So let's say the length of this is 1, and then it's 0.1, 0.1, and 1.2. So, and let's say we need to move 0.5 every step. So on the first frame, we move 0.5. Let me make this red. So we move 0.5 and we're here. And we say, how much space do we have left to move? So the available length left on the primitive. The available length is equal to 0.5. So we move here, like so. And then we say, what's the available length left? Well, the available length left is 0. So then we check on the next prim. Okay, on the next prim, do we have enough length? No, we only have 0.1. We need 0.5. So then we check to the next prim. Do we have enough length? No, our total length is only 0.2 then. So then we check on the next prim. We have a length of 1.2 plus the 2 previous prim lengths, which gives us a length of 1.4. That's enough length. So then we interpolate to whatever position we need to move here on here based on the UV value. And then we increment the primitive index, so it updates to that. So that's what this while loop is going to take care of, and this is the majority of what happens in this wrangle. So in here, I can say int UV, I want to get the UV direction of the next primitive. So this is going to be equal to UV dirs, comma, plus the, I want to grab the current prim index plus the prim counter. And the prim counter is going to be something I initialize out here. I'm going to say prim counter is equal to 1. And the reason I'm starting at 1 instead of 0 is that if the current primitive doesn't have enough length, we need to look at the next primitive. So we're going to get the UV direction of the next primitive just by incrementing the primitive index. So this will increment every time we go through this loop until we find enough. And then we'll say int next prim is equal to prim sequence prim index plus prim counter. So, and then I just want to get the length of the next prim, so float next prim length is equal to prim on the first input, the length attribute, and we're looking at the next prim. All right. So after this, I just need to do a couple more conditionals based on the UV directions. So I'm going to say if the UV next UV direction is equal to 1, so if it's moving positive and not negative, I can say the target UV offset is equal to the step length minus the available length divided by the next prim length, like so. And then the else condition, so if it's negative, I can set the target UV offset is equal to the complement of that, so it's just step length minus the available length divided by the next prim length. But in this case, I need to get the complement by subtracting 1, by subtracting this from 1, like so. All right, so that'll deal with that. And then now I need to check if we still don't have enough length on this primitive, we need to go on to the next while loop iteration and increment the prim counter. So we're looking on, let's say, the third primitive. So we're going to say if the next prim length plus the available length is still less than the step length, so still less than the length we need to move, first we want to increment the prim counter so that we start looking on the next further prim. We want to increment the available length because now we have the length of the current prim or the previous prims we looked at. And then we want to continue to the next iteration. So this will keep continuing until we get enough length. And then once we do get enough length, we want to save the prim index out. It will be itself plus the prim counter. So this will store us the new prim index we want to interpolate the position from. The prim should be equal to the next prim, like so. And then the available length will be equal to itself plus the next prim length, like so. So that's going to handle all of that. And so now we've dealt with whenever the prims are too short. So after this, we need to actually interpolate the position on the curves. To do this, I'm going to create a custom function that I'll call curve UV sample. And it's going to return a vector, which is the interpolated position. And it's going to take a const int the geometry stream and then the primitive number, and as well as the const float u value, so the uv value that we want to interpolate at. All right. So real quick, how this is going to work is if we have a polyline like so, like this, and let's say our start point is here. Let's say this is a UV value of 0, this is a UV value of 1, this is 0.6, this is 0.3. And let's say we want to interpolate at the U value of 0.9. We're going to loop through all the vertices, since the UV value is stored on the vertices, and that way you can have the end points. If you were to store the UV on the points where prims were connected, the UVs would get all tangled up, so we want to make sure we store it on the vertices. So what I'm going to do is I'm going to look through these points. So I'm going to look at, start by looking at the first UV value and then the next UV value, and these are both less than 0.9, so I'm going to go on to the next one, and then I'm going to say, okay, 0.3, 0.6 still less than 0.9, so I go on to the next one. I say 0.6 is less than 0.9, but 1 is greater than 0.9, so I then select these 2 points, and then I interpolate the value in between here, 0.9. So I'll do that by getting the length difference here, which is equal to 0.4, so 1 minus 0.6 is 0.4, and then I can interpolate the position corresponding with the U value. So I'm going to go ahead and write that right now. Make this bigger. So here I'll say I want to grab all the vertices, so primverts is equal to vertices, and on the geo and on the prim is equal to prim vertices. All right. And then I want to create the sample position, and this is the value we're going to return, so I can just say return sample pos. And then in here, I want to say for each int index, int vertex in primverts. And the first thing I want to do is get the next vertex, so I'll say int next vertex is equal to primverts index plus 1, so this will return the next vertex. Then I want to say get the current UV, so vector UV is equal to vertex geo UV, and then I'm reading from the current vertex, and I'll say vector next UV is equal to the vertex with the geo UV and the next vertex. So also return the UV values of the current vertex and the next vertex. And then I just want to get the corresponding point, so I'll say int point1 is equal to, or just to keep the naming conventions, I want to say this int point is equal to vertex point, so get the point that corresponds to the vertex, and the geo vertex, and next point is equal to vertex point geo comma next vertex. And I'll say vector pos is equal to point geo comma p comma point vector next pos is equal to point p comma next point. So, and then I'm just going to do a couple branch statements, and this is going to test if the UVs are greater than. So like I was demonstrating before, I'll start off by saying if the next UV.x is less than U, which is less than or equal to UV.x. And then if that's true, I can get the UV length. So I want to get UV length, which is equal to the next UV.x minus UV, or it's actually the opposite. It would be UV.x minus next UV.x. So this is checking if the UV, when the UV value is reversed, so the UV direction. So I'll get the UV length, and then I want to grab the interpolation amount. So interp amount, this is going to be equal to the UV dot X minus the U value, and then divided by the UV length. So this is the interpolation amount between the 2 points. So then we're going to set the sample position is equal to a linear interpolation between position 1, or between position and next position with the interp amount. And then we can break because we've found the point, and then I'm just going to do the opposite of this for if the UVs are positive. So I'll be saying if next UV dot X is greater than or equal to U, which is greater than UV dot X, I'll say float UV length is equal to the opposite, so next UV dot X minus UV dot X instead of UV dot X minus next UV dot X. And then I will grab the interpolation amount, which is going to be equal to U divided by the UV length. And then the sample pos will be equal to where pos next pos by the interp amount. And then we can break as well, like so. And now if I go ahead down here and just implement this and say vector target pos is equal to curve UV sample on the second input on the current prim, and target UV offset is the value, and then I want to say v at p is equal to target pos. And then we can see the points moved. We're on frame 1, so we need to make sure we're saving out the index first of all for the next frame. So in prim index, so this is just updating it for the next loop or the next frame. The solver is equal to prim index. I want to say f at UV start offset is equal to the target UV offset. So we're updating where we're starting the UV from. And then you'll notice on the first frame, it's already computing some stuff. We want to make sure that we're starting from all 0 values. So I'm just going to say if at frame is equal to 1. I want to set the prim index is equal to 0. I want to set the prim is equal to prim sequence 0. Make sure we're just starting properly. And then I want to check if the UV direction is equal to 0. I want the UV start offset to be equal to 1. So if it's reversed, we're starting from 1. Else the UV start offset is equal to 0, just so we're starting properly on those first prims. And what we should see is that the points are moving slightly, and this is because this needs to be the target UV offset. And I can see because this should be 0 or 1, but it's not, so target. All right, and here we go. And then if I just check, this needs to be in equals. All right, so now we shouldn't see any change, which we don't, so that's proper. And if I go and I reset the sim and I play this back, we should see, boom, the points are moving, and they move within the 60 seconds, which is as specified. So if I switch this different, if I switch this to 240 by the FPS, we should see this now moves all the way till 240 frames. Okay, so that's working perfectly as we would expect. And now I'm going to talk about how to make the trails. Okay, so now I'm going to create the trails. I'm going to drop down a point wrangle, and in the first input drop in the solver, and then the second input bring in the curve network. How this is going to work is I'm going to recreate the primitives in the prim sequence. So let's say this is the primitives from the prim sequence, like so. And then our point is currently right here. So right now, this would put us on index 1, since this is the first prim in the prim sequence, and this is primitive 1. So we're going to ignore all the primitives above in the current or below the prim index, because we don't need those. Those are in front of our curve or behind our point when it's moving, because our point's going to move this way. So we don't care about this. We just want our trail to be x length this direction. So we'll get rid of all of those, and if the point on the current prim is behind, we'll also get rid of this. And then this will be our new point, and then we'll just keep all the points of an x length at the end. All right, so now I'm gonna get started on actually implementing that. First thing I'm gonna do is just read in our variables. So int prim sequence is going to be equal to I prim sequence int uvdirs is equal to I uvdirs int prim index is equal to I prim index f at uv start offset is equal to uv start offset. All right. Like so. And that's all for that. So now we need to create an array called trail points. And this is going to be the series of points. ptnum. This is going to be the series of points that we use to create the primitive. So right now the prim sequence is all of these primitives. We want our trail just to be a single primitive. So we're going to create the points necessary based on the points in this from the curve network on the second input. And then we're going to make a single primitive. So this holds all the points that will be on the trail prim. And after that, I'm going to create an array called int visited, and this is going to keep track of all the points we've already visited, so we're not creating duplicate points on our primitive. So basically, we have the primitives in the second input, like this, the polylines right here, but we have the UV value stored on the vertex, and we're checking the UV value. So on this prim right here, we've got 2 vertices in the primitive, and on this primitive here, we got 2 vertices in the primitive. But both of these vertices right here return back to this point. So when we're looping through here and we're creating a point based on this vertex, this would be point number 0, 1, 2. If we create a point for this vertex, 1, and then we go to it, try to create a point based on this vertex, it's going to try to create that point at the same time. So we're going to store all the points we've referenced from the second stream in this visited array. So if we've already created it, we're not duplicating it. Okay, so that's what that array is for. And then going to add a float value called length counter, and this is just going to keep track of everything, keep track of our length so that we can cut off the trail. So to do that, I'm going to create a float called trail length, and this is going to be equal to a user specified channel trail length, like so. So this will just be the physical length of the trail. Okay. And after this, I can say loop through the primitives and the prim sequence. So for int I is equal to the prim index. And we're starting at the primitive index because we don't need any prims that are behind that. We're not creating those points. And then I is less than the length of the prim sequence, just increment. And then in here, the first thing I want to do is get the primitive. So I'll say int trail prim is equal to the prim sequence of I. And I want to get the points, so I'll say int prim points is equal to prim points 1 comma trail prim. I also want to get the vertices, since that's what we're gonna loop over to get the UV values that are stored on the vertices. Prim verts is equal to prim vertices 1 comma trail prim. So and I also want to get the UV direction, so I'll say int trail uvdir is equal to uvdirs I. Okay, so from here, I'm just gonna say if the trail UV direction is equal to 0, so that means if it's reversed, and then I want to reverse the arrays. So I'll say prim points is equal to reverse prim points, and prim verts is equal to reverse prim verts. So if the UVs are backwards, we reverse the array so that we're going through it in the proper order always. And then after this, I'm going to create a uninitialized vector called last position, or last pos, and we're going to measure the length, increment the length counter by the distance between the points, or in this case, the vertices, which will get the points from the vertices and then compute the distance. So we're going to be going by segments this time, not by primitives. And then after that, I'm just going to say if the I is equal to prim index, so if it's the first primitive, last position will be equal to the current position of the point, and then else the last position will be equal to the point attribute position from 0. So what this is going to be doing is this is just initializing the last position value for every primitive. So it will always be at the start point, just so we know where we're starting from. And then I'm going to loop for the vertices now. So I'm going to say for each int vertex and prim verts, I'm going to get the last point. So I'll say int last point is equal to trail points minus 1. And then I'll get the current point. So int point is equal to the vertex point 1 comma vertex. And then I'm going to get the position is equal to point of 1 key comma point. And I'll get the UV value. So vector UV is equal to vertex comma UV comma vertex. Okay. And then now I'm going to skip all the points at the front of the primitive. So I'm just going to do that in conditional. So I'll say if the trail prim is equal to the prim sequence prim index. So if we're on the first primitive, and if the trail UV direction is equal to 1, so it's positive, and the UV value is less than or equal to the UV start offset, then we can just continue and we won't create any points or anything. And then the same, say else if the trail UV direction is equal to 0, if it's negative, just do the opposite, UV dot x is greater than or equal to UV start offset, we will continue. All right, so that'll just deal with those points at the front, ignoring them. And after that, I'm actually gonna create the points. So I'll say if find and visited, and the point is less than 0. So if we haven't already created a point that corresponds to the point in the second input stream, which is the curves, then we can create the point. So I'll get the segment length. So float segment length is equal to the distance between the last position and the current position. So this is getting the length between the 2 points so that we can increment. And then I'll say if the length counter plus the segment length is greater than trail length. So this is if it's greater than the trail length, we're going to have to interpolate the position to create a new point at the end, so we're not just stepping based on the uneven segments. But before that, I will just handle what happens if we're just in the middle. So here I'm appending the point to the visited because we visited it. Here I'm going to create the new point. and it's going to be on 0 from the position. And I'm going to append this to the trail points with the new point. And then I'm going to increment the length counter by the seg length. And then the last position will be equal to the position. Okay. And then after this, I want to start implementing the length counter. So here you can see we've added the points. We just haven't created the primitives. And I can go ahead and create the primitives outside of here. I'll just add the new prim. So I'll say int new prim is equal to add prim. So this is the trail prim. It's a type polyline, and we're using the trail points to create it. So it takes a little while to cook, but you see we've created the corresponding trails, and it should, you can see they do move according to where the start. So all we have to worry about is cutting off the end now. I'll handle that in this if statement. So I want to create an interpolation amount, and this is going to be equal to the trail length minus the length counter, and then divided by the seg length. So this is getting the percentage between the 2 points that we need to interpolate the position at. And then we'll say vector end position is equal to a linear interpolation between the last pass and the current pass by the interp amount. And then in endpoint is equal to add point 0, comma end pass, and then I'll append trail points to the endpoint, and then I will break. But then I also want to break out of the while loop that we're in, or this this for loop, because right now we're just breaking out of this for each loop. So I want to create a variable outside here called stop. I'll just say int stop equals 0, and then in here I can say if stop equal to 1 break, and then in here I will set stop equals to 1. All right, so now we can see that our trails are getting cut off by this amount right here. So if we set them to be really short, like so, I'll set them to be right here for now, we can see that we have our trails moving appropriately. All right, so that's all, and I hope this was helpful.